Welcome to week 10 of computational quantum chemistry. So this week we are going to discuss about excited state methods. Up to now whatever we have discussed is about ground state method. So today is the first time we are actually going into the excited state method. Now the excited state methods are one of the most interesting areas of quantum chemistry, quantum mechanics, because it has implication in many of the real life processes for like our vision, photosynthesis, many of the processes which happens actually in the nature actually go through an excited state method. The second thing is that there is no clean method which can give you very sufficient accuracy in the excited state. The couple cluster method, which is generally considered as the gold standard of quantum chemistry, that's only for ground state. Excited state couple cluster method exists, but their accuracy is not so high as a ground state. This is not to mean that the excited state couple cluster methods are less accurate. They are accurate, but at the singles doubles truncation or even with the perturbative truncation, it cannot lead to the kind of accuracies what a ground state method will give. More problematic thing is that there are various kinds of excited states, and it's very few excited state methods which actually works for all of them. So that's another problem. The third problem is that the DFT, which was found to be a good alternative for ground state, may not be as accurate as couple cluster, but when you think of comparison and comparison of the computation cost and accuracy, DFT has came up as one of the best possible alternatives. But the DFT method's performance for the excited state is dicey at best. It will work for few excited state, it may not work for certain excited state, and there is no Wien-Bergkuhn theorem for the excited state. So, from theoretical point of view also DFT has a problem here. So, let us dive into the excited state methods and try to understand how it is. So, let us start with a very simple 3 electron system, lithium. Why I choose lithium? Because here it is possible to draw all the possible configurations. So, this is my lithium Hartree-Fock reference state, molecular orbital. Now, these are my configurations. So, I can get singly excited configurations out of it, where one electron is excited. It can be excited from the singly occupied molecular orbital as HOMO or from the doubly occupied. There can be doubly excitation, where 2 electrons are excited at the same time, as well as there are triply excitations, where 3 electrons are excited at the same time. Now, if I take all the possible configuration, of course, that gives me the exact wave function and energy for that particular state, because that is within that, of course, within that particular basis set approximation, because that will be equivalent to the full CI solution. It is a minimal basis set lithium, 3 electrons and 2 virtual orbitals. So, I can generate all the possible configurations and that will give me the full CI. Now, for the ground state, we know that the singly configuration excited configuration itself does not have any contribution as it is because of Brillouin's theorem, but if I consider the double excitation, I can also get the singly excitation get coupled to it, and also I can get triple excitation. However, for excited state, only singly excited configuration can give you a certain kind of excited state. Remember, when I say that this is a singly excited state, doubly excited state or triply excited state, most of the cases what I mean is that the particular wave function is dominated by singly excitation, and the single excitation may not be only one excitation, but it will be a linear combination of all the excitations. Similarly, when I say the excited state is dominated by double excitation, it does not mean that it does not have any contribution from single excitation or triple excitation. It definitely have some contribution, but the contributions are generally small, and the dominant contribution actually comes from the double excitation. And it may not be a single double excitation, it may be a linear combination of the double excitation. And when I say that, maybe for single excitation, when I say that it is a HOMO to LUMO excitation, for example, this one is an HOMO to LUMO excitation, it does not mean that this only consider this configuration. This actually is a linear combination of all the configuration, where the HOMO to LUMO the coefficient of the HOMO to LUMO excitation is actually dominant. So, that is what we mean. We say that it is HOMO to LUMO, but what we actually want to mean is that it is dominated by HOMO to LUMO excitation. Now, when I consider the excited state, of course, the ground state does not have any contribution. So, the first contribution to the excited state actually, because I am working with a linear Hermitian operator, and ground and excited state configurations are orthogonal to each other. So, when I talk of excited state, my first possible and the simplest approximation what it can come is from singly excited configuration, and that leads to me configuration interaction singles or CIS. The methods we have considered so far treat the molecule in the ground state, the lowest energy configuration, but because CIS is a configuration interaction method, the mathematics built into the ground state method has the feature of trying to optimize parameters and minimize the energy. That is for any variational method, and they will require additional constraint to solve for other stable electronic state that are not ground state. And the first approach to express the excited state as a sum of singly excited determinants, which are known as CI singles method. And so, what happens is that if I think of the Hamiltonian matrix elements, so this is Hartree-Fock, this is singly excited configuration, all the possible singly excited configuration, and if I consider the matrix element, of course, because of the Brillouin's theorem, there is no coupling between the singly excited to singly excited configuration and the ground state Hartree-Fock configuration. The coupling is off diagonal coupling blocks are 0. So, that means I can diagonalize them individually. But the singly excited space is actually coupled. So, what you should do here is that you should do a diagonalization, and this diagonalization will give you all the excitation energy starting from the first excited state to the highest excited state configuration. And in minimizing the energy with respect to the T1, it is assumed that the collapse to the ground state will not occur, since the Hamiltonian integrals relating each single determinants to the ground state is 0 as a result which is known as Brillouin's theorem. In some of the cases, this expression is written as R. The TR and R's serve the same purpose, they are the singly excited amplitudes. And if you think that we have used the notation T for couple cluster amplitude, whereas we are using C or R for the CI amplitude, CIS can be also called as a CCS. In some of the cases they are used, they give you identical answer for the excitation energy. Now, the level of theory is variational, so it will always lead to an energy above the true energy. Now, the problem is that you are only having a singly excited state. That means this is your 0th order contribution to the excited state. So, I am starting with an Hartree-Fock orbital, and CIS just allow me to get to the excited state. My orbital relaxations are not treated so much. So, one way to repair CIS, of course, I can consider the double excitation, and that will repair the problem of orbital relaxation, but that will increase the computation cost also. So, one way to repair the CIS without adding substantially to the cost of the calculation is to allow the CIS wave function to partially relax by introducing de-excitation amplitude into the expansion. And so, this is how will look like, where A is a CIS kind of expression and the B matrix is same size and contains the Hamiltonian term relating to the determinant formed by a single excitation on one side and single de-excitation on the other side. So, this B matrix actually brings into the effect of the de-excitation process. So, it brings the orbital relaxation a little bit more. Generally, the effect in the excitation energies are very minimal, but because it relaxes the orbital, the wave function actually becomes significantly improved. So, excitation properties, transition properties, excitation energy dipole moments, sometimes polarizabilities actually improves quite a bit. Now, solving this eigenvalue equation leads to the excitation energy omega and a vector of excitation and de-excitation amplitudes. Now, this theory is known as a time dependent Hartree-Fock. It recovers some of the electron correlation missing in the CIS picture at the basically same computational cost. The time dependence in the name comes from the fact that fundamental equation of these methods are ultimately derived from time dependent Schrodinger equation. There is a typo here. The derivation relies on the linear response theory. I will not go into the details of the linear response derivation of the CIS singles. It is too much theory. If you are interested, there are nice literatures available. If you set this B matrix to the 0 in the previous slide, that leads to CIS singles. A much more accurate approach is to incorporate density functional theory into the time dependent formalism, and a time dependent density functional theory or TDDFT can be derived in an analogous way to TDHF using a density functional. and the A and wave matrix then can be evaluated using Kohn-Sham orbital from a DFT calculation. The excited state that emerges will include exchange correlation effects as well as the flexibility coming from the time dependent approach. So, it not only can get that excitation energy and the slight amount of the orbital relaxation, because I am using the DFT orbitals. So, it contains the exchange correlation effect to an extent also. But remember, this is like an hodgepodge treatment. First of all, there is no Hornberg-Kohn theorem for the excited state, it is only for the ground state. So, it is derived like a perturbation to the ground state wave function. So, that is why it is one of the pitfalls of the DFT is for excited state, because the theory is not very clean in this case. Now, let us do the first calculation. So, let us take a very simple molecule, formaldehyde, and we are going to do the calculation. So, see the keywords. So, for doing excited state calculation, I need to give a percentage CIS block. I want to calculate 10 roots, n roots is equal to 10. Depending upon how many roots you can give. So, if you are doing CIS, so the maximum number of roots possible is number of occupied times number of virtual, but if you give so many roots, there can be often convergence problem, and in most of the cases the very high lying root are actually not so accurately described. Of course, when you are trying to do core excitation or X-ray spectroscopy simulation, they are generally very high energy, but you need special techniques to describe them. We will come into that, what kind of special techniques you need. As a standard, we are using RHF, we are using a triple zeta quality Popel basis set with 2dp. RIJ cos we will use to reduce the computation cost. I want to see the molecular orbital, because one of the important things here is to how to interpret this excited state, and that is actually a tricky job. So, we will carefully see the molecular orbital to interpret the excited state. Remember, one of the major use of excited state calculation is to calculate UV visible spectra. Now, UV visible spectra, of course, you can measure in an UV visible spectrometer. Many of you have already seen it or may have done this experiment yourself. Why it is important to understand the look at the molecular orbital and try to understand from which orbital to which orbital they are going, because one of the major purpose to do this excited state calculation is to do the interpretation of that UV visible spectra, and for that it will be very important to have this one. So, you will be using the large print keyword, and this geometry is not optimized, I have just prepared using ChemCraft. So, let me go to my notepad. I save it into week 10 and let me put it as H2CO.INP. So, to look at the orbital and to see how the spectra looks like, of course, we have to open it using ChemCraft, but before opening into ChemCraft, let us look at the output file very carefully, because there is much more information than the graph what we have seen from the ground state calculation. Okay, the use symmetry keyword is here because we want it's often very easier to interpret the state if we use the symmetry symbols, and you can guess why certain transitions are allowed and certain transitions are forbidden. So, the symmetry of this system is C2V, and if I come down you will see the irreducible representation. There are 4 irreps, each one dimensional, A1, A2, B1, B2. I will not describe why they are called A1 or A2 or B1 or B2, you should consider any good group theory book for that. So, after your SCF is done, these are the orbital gas. Remember, we have given large print because we are interested in seeing the molecular orbital. So, this is the ORCA SCF. So, here it is given the symmetry of the each orbital. So, again these are molecular orbital printing, because of a large print there is so much printing in the output file. So, this is how the CIS calculations will be done. So, this will be solved by a Davidson diagonalization procedure, and because I am doing in a CIS space, so dimension of the max eigenvalue problem is 360. Why it is 360? Because remember I am dealing with H2CO. It is basically a 16 electron system, and let me see the number of virtual orbitals here, maybe we will be able to make a guess. So, it is 16 electron, and so it is from 0 to 68. So, total number of virtual is actually 60 in this case. And we are going to remove the core electron. So, my total space dimension will be 300, sorry, my total space dimension will be 360, because it is a 60 into 60 dimensional space what we are diagonalizing at. So, number of roots determined will be 10, and generally it is 10 times the maximum subspace. So, this is what, so this diagonalization is not done using a full diagonalization. To do the full diagonalization of a matrix, maybe 360 dimensional matrix may be still okay to diagonalize. It is sometimes very matrix, if your molecule size is very big or your basis set size is very big, it can be an intimidating task to diagonalize the full matrix. So, what we will do is that we will start with a guess and we will do an iterative diagonalization. That is why it is doing this kind of iteration, and these are solved by Davidson diagonalization problem. For most of the TDDFT calculation, you will never see a diagonalization problem in the calculation, and the iterations will generally converge, but there can be an isolated cases if you are targeting certain special root or very high lying orbitals, sometimes these iterations may not converge. Of course, full diagonalization does not have that kind of a problem. Second thing is that this is how the output will look like. So, you can see the transition orbital, these are basically the normalized value, because remember the excited state also needs to be orthonormalized. So, one important thing to notice here is that how you see the symbols. So, there is a state 1, this is the first state, it gives the excitation energy values both in atomic unit, electron volt and centimeter inverse. The expectation value of the square operator is 0. So, this is a singlet state, and symmetry of this, and of course, multiplicity is 1, that you should be able to see from the square value also, and symmetry of this particular state is A2. And the dominant transition, so you can see that there are multiple transitions there. As we are discussing that when I say it is a particular transition, it is not that that is only one transition. So, this wave function for this state is actually obtained by linear combination of 3 transition. So, 7 is the HOMO in this case, and this is LUMO plus 2, and this is LUMO plus 4, and this must be LUMO plus 10. So, these 3 so these are the dominant transition in this case. There are many other smaller transitions which are possible. So, this transition actually has the highest coefficient. So, I will characterize this state by looking at this kind of this transition. For the second state, this is state, this is the energy, this is the symbol is B2, this is third state is also B2, fourth state is A1, like that it will go on. So, after this transition has been done, to calculate the, remember calculation of the excitation energy only gives you one part of the puzzle. For the other part you need the corresponding transition property, and the transition property you can calculate using both like you will need to calculate the oscillator strength, and the oscillator strength can be calculated both at the velocity form or the dipole form of the oscillator strength. Remember, transition the wave function actually in this case does not have any significance. It is the square of the wave function expectation value which actually leads to oscillator strength. So, if you look at the dipole formalism, which is generally more commonly used, you will get this transition dipole moment x, y and z, but the experimental observation, the absorption coefficients are related to oscillator strength, which is square of the transition dipole moment values. Now, if you want to see these transition dipole moment values, you will see that in certain cases the transition dipoles are 0 and in certain cases they are non-zero. Now, this if you look this thing with in conjugation with the group theory, you will see very interesting features. So, think of this transition dipole moment integral. So, this symmetry is 1 A1 to 1 A2, that means my effective symmetry of the ground and excited state wave function, total wave function will be 1 A2. Now, to give a non-zero transition moment, your transition dipole moment should have, so the total value of the integral has to be totally symmetric, that is 1 A1. So, if I multiply the ground and the excited state wave function, ground is A1 A1 and the excited ground state is always totally symmetric. So, it is always 1 A1. So, my excited state is 1 A2. Now, to make the transition dipole moment to be 0, the transition dipole moment has to be aligned along the rep A2, but along A2 there is no transition dipole moment. The z and x and y is along A1, B1 and B2. So, there will be no transition moment in this case. Look at the second excited state. Ground state is always 1 A1, excited state is 1 B2. So, the transition dipole moment will be only 0 for the case for the direction which is aligned along the rep B2, which transformed according to the rep 1 B2. Align is not the correct word, it transform according to the rep 1 B2. In the case of 2 B2, they are actually along the y direction. See, for the 1 A1, the ground and excited state is 1 A1. So, the dipole moment will be along the transition dipole moment along with direction which transform along 1 A1, this is z. So, in this case also it actually has the z component actually has non-zero transition dipole moment, and that is what leads to oscillator strength for this 3 mode, where the first excited state will not have any oscillator strength. Similarly, you can get the CD spectrum out of it in both formalism, and this gives you the timing and all other things datas. Now, what we will do? We will open it with Chemcraft and try to visualize the UV visible spectra, look at the orbitals of each transitions much more carefully.